Okay, I got sidetracked in an unsuccessful experiment for organic chemistry, the big fat zero. So, on to this, now that my phone is recharged. We are on page 213, 6C, I think. And how long would the car in sample problem 6C come to take a stop? Come to a stop from 20 meters per second to the west? And how far would the car move before stopping? Okay, so apparently you have to take the force, and we're looking for the time, and it was going at 20 meters per second to the west, which I called negative. That's my initial velocity. So my final velocity is 0 minus initial velocity for delta V. So that's going to come out to be positive, and my mass is 2250. And that will come, if you've got this amount of force, it'll stop the car in some amount of time. If it's got this much mass. If it has more mass, it takes longer. The time comes out to be 5.33 seconds. And that's why they mean by how long would it take. Okay, now you have a few options for how you're going to figure out how far that is. One is you could do this all the way back from the beginning of school. You don't know what the acceleration is, but you know what the maximum velocity is. And you can put that over time. And then you'd have basically, well, I'll show you over here what you'd have. So what you could do is put time in there and your initial velocity, which was 20, and then you've got two unknowns. So then you need V equals V sub 0 plus AT also, I guess. So I'll probably have to add this in here because I was doing that substitution in my head. But V final is equal to V initial plus A delta T. So this isn't a good way to do it. But if you put your two velocities in there, you have A and delta T you got to look for. And then this equation, you don't have A and delta T. But at least you have two equations with the same two unknowns and you can substitute. An easier way to do it would be to use the equation velocity final squared, which is 0, equals velocity initial squared, which is minus 20, plus 2 times A times delta X. But again, you don't have A. But if you say A is delta V, subtract these V's, divided by delta T, delta V divided by delta T, that's what A is. Well, that's also slope. You can find delta X that way. It comes out to be 53.3. The way I would prefer to do it, rather than slog around with those, is just make a little velocity time graph. Acceleration is constant, it's a straight line, it's decelerating, it starts at 20, goes to 0, takes 5.33 seconds. Y equals mx plus b isn't going to help you here because you already have b and x and y and m. Well, it's the only thing you don't have. Use area, which is distance, is 1/2 base times height, so you have 1/2 the base is 5.33, height is 20, and you've got it. You're done. Comes out to be 53.3 again. Okay. Well, back to really a impulse equals momentum problem. And number 3 says, assume the car is 3,250 kilograms, so we make it 1,000 kilograms heavier, and we want to know what the force is like. Well, when you subtract that and multiply and divide, it comes out to be 12,200 newtons. Now, then it asks about, well, how far would the car move before stopping there? Well, it turns out that it's going to go the same distance because velocity initial and velocity final are the same, and acceleration is the same, which means the time is the same, and means the graph is the same. So none of the rest of that changes. All you did was increase the mass and increase the force, and if you put the force over the mass, you had the proportional constant with the same acceleration. So none of the rest of the graph changed. So the solution back here on page 2, if you tried to work it out for problem number 1, it ended up being the same solution for problem number 2. Okay, number 3. A 2,500 kilogram car traveling to the north, we'll call that positive, slowed down from an initial velocity of 20 meters per second by a 6,250 Newton braking force opposite. Answer the following questions. What's the car's velocity after 2.5 seconds? Put that in the equation. And force, time, velocity change, 2,500 kilograms. We're looking for the ending velocity, so it's final minus initial. We have the initial. And if you do that algebra and you solve for velocity final, it comes out to negative 14.0 meters per second, which is to the south. And then B, how far does the car move during the 2.5 seconds? We're back to the same, the same solutions. The difference is on this one's a little easier to use what you're used to. I just took the 6,250 and 2,500 kilograms and used F equals ma and found A. And then you've got A and T and V, so this is real easy to do. The change in X comes out to be 42.2 meters. Going on to the next one. Page 214. The speed of a particle doubles. Oh, well, here on this one, I was just showing that, well, you could use the graphical solution on this one too. Yeah, put your 2.5 seconds out here, put your initial velocity is 20, your final velocity is 0, find the area under the graph. It's going to come out to 42.2 again. On number 3, C, how long does it take the car to come to a complete stop? That's in time. So you take your 20 minus 0, your m's 2,500, your force is 6,250, comes out to be 8 seconds. Okay, now number 1, page 314. If the speed of a particle is doubled, the mass is the same, so you're just doubling your answer for momentum. Your momentum becomes double. If your kinetic energy is, or if your velocity is doubled, what happens to your kinetic energy? Well, 1 squared is 1, 2 squared is 4. So if you double your velocity, the momentum goes up by double, but the kinetic energy goes up by a factor of 4. If this velocity is tripled, the momentum triples. The velocity goes up by 3 squared, 9 times as much. Pitcher claims he can throw a .145 kilogram baseball with the same momentum as a speeding bullet. So the bullet's 0.03 kilograms going at 1,500 meters per second, which is quite fast. That's supersonic and then some, because 343 meters in a second is speed of sound, so this is a supersonic bullet. What must the baseball speed be if the pitcher's claim is to be valid? So let's set these two momenta each equal to each other. So you got the bullet's mass times velocity, baseball's mass, solve for velocity, comes out to 31 meters per second. So that'd be, I don't know, 25 meters per second is 55 miles per hour. So that's probably a 70 or 80 mile per hour pitch. So yeah, some pitchers can do that. Number B, which has the greater kinetic energy, the ball or the bullet? Okay, well the ball is 0.145 kilograms times a half times 31 meters per second squared, which comes out to be about 70 joules. I'm not sure that number is right. That seems awfully low. I'll have my calculator out. But the bullet's is much greater because the velocity of the bullet is much greater. Square 1500, that's a large number. 31 times 31 times 0.145 times 0.5. Yeah, 70 is okay for the baseball. Okay, number 3. When a force is exerted on an object, does a large force always produce a larger change in the object's momentum? And explain. No. Because think about an ion propulsion system on a spacecraft that's moving through the solar system, and an ion propulsion system might exert the force of the weight of a piece of paper. But if it's pushing a 3-ton satellite with this force under no friction, essentially, at a very low acceleration, but day in and day out, 24 hours a day, 365 days a year, it can wind up being a very high change in momentum. So a small force exerted over a long period of time could result in a larger change in momentum than a large force exerted over a short period of time. And number 4, what's the relationship between impulse and momentum? Impulse is equivalent to a change in momentum. Number 5, 0.42 kilogram soccer field's moving downfield. A player kicks the ball so it has an final velocity of 18 meters per second downfield. What is the change in the ball's momentum? Well, it starts at 12 meters per second, ends at 18, so that's a delta V of 6 meters per second times 0.42 kilograms is 2.52 kilograms times meters per second. Find the constant force if the two are in contact for 0.2 seconds. So if this change in momentum is force times delta T, just divide and multiply by 50 basically, and it's 152 newtons downfield is how the force was applied. Okay, if we were to go on, we would get into conservation of momentum, and that's kind of a change in topic. So I have for you 2 or 3, I have to look them up, videos for you to watch sequentially in order that show things about the relationship of power and force and acceleration and momentum and kinetic energy and velocity and displacement. So watch those. This video should be, I want to wrap it up here, Physics26BBlake.